in 2016, 16 for his single molecule motor or something like that. Yes. Then he did postdoctoral in Japan for 2 years. Then he moved to Singapore. Then did a as a senior researcher for 7 years, mainly developing advanced surface characterization. And this is probably that we will hear. Dr. Arramel now works a lot with perovskites. So for those of you that don't know, perovskite is one of the emerging materials nowadays. They use it for solar cells. It is predicted to replace silicon because it's really growing quickly in efficiency. But then also Dr. Arramel and his collaborators in Poland, Dr. Danang, I think he visited us, but not to physics, but he visited UE six months ago. Work a lot on using perovskite for new, totally different application that is for scintillators. Scintillators is basically, what is scintillators? Yes. So it is a really emerging materials. It will develop, I guess, very rapidly, I think, the coming years. And Mr. Aram is one of the main researchers in this field. So without further ado, I hope you will get something from this talk, and hopefully can learn. And Dr. Aram, please, the time is yours.
Thank you, Ferry. Assalamualaikum warahmatullahi wabarakatuh, and good afternoon, everyone. Will try to do at my best. Just help me out a bit, Ferry, if I should say, losing canon by avoiding the time limit. So help me out a bit in case I'm surpassing the allocated time. As Ferry said, it's a great pleasure to come back to physics department of Universitas Indonesia. Been here for a while, like actually last year. Our lab was planning to buy a Raman spectroscopy, and then we figure out that here in physics department has a Horiba spectrophotometer that as one of our candidate to pick which kind of manufacturer we would like to buy, and then did try a bit trials with our samples. So today, based on the invitation letters, the team itself tells a bit about exploring interdisciplinary frontiers in physics. So I'm not actually originally have physics roots. I was a bachelor student once in 1999 till 23. But I did have a bit of flavor when I took my graduates in top master and science program, so a bit of physics there. So today I'm gonna give you a bit an overview of how we can utilize two techniques. It's not so sophisticated, but it has its own infancy. So I hope by the end of this afternoon, all of you can know about what is soft X-ray absorption spectroscopy, and pretty much I hope you guys actually know better than me about photoluminescence. So this is more like an hour or so crash course on these two techniques. Yeah. So before I start, let me show you our office. The location itself is not too far from here. So it's roughly about 50, 60 minutes. If you took a nice freeway from Serpong Cinere, it just give us a bit of time. Actually, I come a bit earlier, but I need to break myself to handle some of my students having some chaos in the lab. So I spoke for a while with them. The time from our office is quite quick during not rush hour. But if we go a bit earlier, I don't think we will manage in time like what I promised to you. So this is the overview of our office. The location is not very far from the main gate of BRIN, our largest research institution in Indonesia. It has a 4-story level of buildings. Was built, I think, in 2021. And then we start filling the office at the beginning of the year. And I come to the office after I finish my previous project, just for a quick promotions. This is my lab, so-called applied physics and chemistry. And this is our latest website. So I do have one freak student who like to make a website. So this is actually already like the third one we made. So he's like to do some experimentation of making a new website. So I give him some of the degree of freedom to play, and he come out with this latest promotion. Hopefully, you guys can take a look and check out later. So for those that have been very mentioned earlier, I've been wandering around throughout the globe for the past couple of years. It all started. I was a chemist student back then, and mostly working in chemical synthesis. But for my final project, I'm doing some more like being care or become environmentalist. So I did some work for my final project, working on handling our laboratory waste. So we only utilize simple acid-based treatment to overcome our excessive amount of lab wastewater. And then after I finished my graduate, so I fly away to the northern part of Holland. So I'm working my MSc and PhD for there for in two different respective groups. First group working under Professor Tom Pasa, working in the group of solid state chemistry, growing some of actually perovskite back then, simplified design. And then after that, I switched to physics, working under two great professors in the institutes. Those are who are familiar with quantum conductance in gallium arsenide, maybe know a bit about the name of Bart van Wees. So I was working under his helm for my PhD, along with Ben Feringa, the Nobelist from the chemistry part. So afterwards, I jumped to Japan for 2 years. There, I just like working as an instrument engineer. We built some four-port STM, not so very successful, but due to the time limit, we're almost half the way of the project. And then before coming back home, spent for about 6, 7 years, 6 plus, as an research fellow under the work of Prof. Andrew Wee. There, as Ferry said, my main concern is how to utilize surface spectroscopy, and therefore, I made some interaction with Prof. Andrew Rushdie, who has some access to Singapore synchrotron, that most of the experiment come from that particular lab. And then now I'm working as a group leader and also research development manager in a company, Nanotech Innovation Global. So actually, NCI is just a research institution, but the funding agency who provide us the budget comes from Nanotech Indonesia Global. So it's a public company. Okay. So before I start with the material, I always start with how we show a deepest gratitude to our friends and colleagues who helped us to come with the nice story in our published article. So these are the three, I call it three little gangs. Most are basically Indonesians. And as Ferry said, this is our big boss in Poland. He is now a group leader in photonic material research team in Port. Is a one of the large research institution in Poland. In the middle one is Haris Mahyudin. He is now acting as a group leader as well in the base of density functional theory. So he helped us a bit about how we can calculate our subject of materials. And the left-hand side is my fellow classmate in chemistry. Yuli is now as a chemist lecturer in ITS Surabaya. And these two friends over here is Chisin and Sinmao, who now one is Sinmao now is working in Shanghai University as a professor in physics department. And my colleague here is a Singaporean. Chisin now still working in Singapore Synchrotron Light Source. And some of our external colleague here, you can see some are scattered from a domestic university, and some of them also foreign campuses. Okay, now let's go to the story. I hope today can give you a bit of some of the points over here, which is mainly discuss our discovery on three different aspects how we utilize a perovskite. first thing first, we try to come out with an idea how we can demonstrate an indirect observations of a small polarionic state in ionic liquid based system. On the green part, there is some bit of philosophy. That's why I put the green there, because we try to come out with a replacement of lead as the content of the perovskite. So therefore, we choose to have some interest on using cobalt as our metallic center in one of the topics that I will discuss today. And last but not least, is blue. Again, spirit of environmental case. We bring up an idea how we try to push the limit of a copper halide perovskite. So this material is not entirely new, but we try to find a small contribution there. And this is just only some a bit caricature I say about how three things that I hope I can give you a bit of an impressions what is our activities there in NCI and our team. Yeah, short about NCI. Nano Center Indonesia is a non-profit research institution, and therefore we try to look a bit on the past, what people have done so far. So it starts in a community basis. So before we found our startup company, Prof. Nurul and also Alfian Novianto established a community under their small place in Serpong. Back then in 2005, they developed an idea of creating a company in which we can actually find an application all in terms of nanomaterial based technology. And throughout the time, it all started after the first incubator in back 2013 was founded, so-called Nanotech Herbal Indonesia. And then later on, after this is the long name, but we want to make things more simplified, so we call it NCI. It's much easier. So at the 2020, the company was found, so-called Nanotech Indonesia Global. And then in 2022, we rebrand the name, which much more easier and much simpler. So we call Nano Center Indonesia. And in our research institutions, there is 4 different respective team, mainly working in different interests. So first is Buetik. Buetik is working in the Center of Excellence, discussing about life sciences. So all discuss about how her team try to come out an idea how to produce a product that be applicable by using our natural resources. And one of our key figures in the company is propolis. And myself acting as a group leader in a team of applied physics and chemistry, we mostly have some interest on fundamental understanding how to really figure out the interrelationship between the structure and property. And Alfian Novianto now is handling the discussion about the advanced material. So he and his team mainly work on the how to use, for example, his interest in ceramic technology, and some of the team working on the application of ball milling technique. And Prof. Nurul is mainly working in more applied interests. So he has like 4 different team, the largest group team ever in our institution. So he subdivided into 4 different research topics. Yeah. So now talking about my team in APC, here we have 4 different sub research cluster. The first one is currently Ande. Ande is and his team working. He has some chemical engineering background. So with him, we try to figure out how to use our core technology in our development. We would like to use the generation of nanobubble as one of the alternative in wastewater applications. And now Ande is currently pursuing his study in Imperial College London. And Ajis Yudo Wijoyo is a petroleum engineer. So mostly we want to find emerging situation in which we can try to use technology and his expertise. And currently we try to find a way in his expertise to use a nanomaterial as an active agent in recovery oil. So the idea is that most of the oil underneath in this offshore have some issue. We cannot really maximize the extraction point. So by incorporating the nanomaterial agent, hopefully we can increase the efficiency of the extraction. So that's the in a nutshell. Sri is working on application of electrospinning technique. So her interest is basically to use this technique to formulate nanofibers, and our application are mainly broadened to for water filtration all the way to the environmental remediation. And this the last team is basically one of that been routing for so far is now is technically undertaken by Afif and the team. And we mainly has some interest that today all the story will be dedicated on this particular subject. So as an highlight, the team itself was built almost 2 years ago. And this is one of the things that we like the most. Oh, sorry, is we help a bit. And one of the big paper that Danang is aiming for the past 3 years, how we can actually figure out to integrate a plasmonic to enhance the pulsar effect uh, in ultrafast and high livelihood perovskite scintillator. So the whole idea is quite simplified in this graphical abstract in which we introduce a thin metallic space in between the ultrafast scintillator and our substrate. And I think this is quite how to say agony because I try to follow the peer review process. It takes like 3 or 4 rounds if I don't mistaken, and the referee just keep buzzing us with some silly question that we discussed earlier with Ferry. So pretty much we are quite busy in terms of numbers, but I don't want to become like how to say crazy people that push the student just numbers and numbers. But we try to ask them to uh, uh, quite effective because all this work this basically is a teamwork. We cannot never achieve this kind of a situation in which we don't know people. So my suggestion to the young fellow student, well, just keep talking and find a new way to create and enhance the number of the networks because this is how to say is an accumulation after several years of branching out, meeting a lot of people, and then we can end up with this kind of outcome. Okay, so before I start, for those who are not familiar with perovskite, let me give you a brief intro. I always start with this paper because this paper gives you an understanding how we can utilize perovskite. Perovskite itself has different dimensionality, or let's say different construction. And the easiest way to understand that most are basically based on the hybrid case. Hybrid means the combination of two different entities. One has an organic side and the other one has an inorganic part. And in the case of classification based on the dimensionality, you can tell already that it has a very myriad design. So you can tell that we can start working on a scale of 0 dimensional represented by a formation of quantum dots, or you can also work in nanoparticulates like having a 2D class of a hybrid system and henceforth. Yeah. So this, in the chemistry point of view, how one can distinguish all these things. I always ask my student, well, try to be picky and then find some trends on it. So usually for those who are already quite reading a lot of papers on 2D, they can already spot an example that, okay, if I see this kind of chemical system, then I can tell this is 2D. But again, you just need to read a lot. Okay, so before going into deeper, let me start to give you a flavor of what is rational design. In protein engineering, this technology has been widely used, and a rational design is essentially give you an idea how you can find a strategy creating of a new material with different type of functionality, because this is very important. And then why is it so important? Because it takes ages. And then luckily nowadays, in the era of AI and machine learning, this help us a bit to predict, because that's the main message of this kind of concept. Once you be able to simulate, or let's say to have an idea that your predicted chemical structure will give you the targeted functions, then it's gonna save a lot of times. You don't need to bothering much during my cohort back then. You really need to dig a lot of textbooks to get an idea. I need to get this kind of certain function to give you, for example, hydrophobicity. Back then, I have no clue because you didn't need to read a lot. But with machine learning, everything goes like going to the expressway, fast as an F1 car. So that's the good thing with rational design with this kind of new technology. Yeah. Okay. So to give you an idea how we grow the perovskite, the whole thing is basically simple wet chemical synthesis. So we pour several of our precursor, and then I will say, well, depend on the structure. Some of the case can be grown for only about 6 days, and then to get such a nice large crystal, there is some post production to get a good transparent crystal. So to have this large crystal of this kind of a chemical structure, the API SN2BR10 takes us struggle for about 3 weeks time. But it's really how to say worth it to continue, because this crystal give us a very good physical properties. On the other hand, some of the case is quite relaxed. For this kind of structure, the PE to copper chlorine is much easy to grow, but you just need to be patient. So this one about 2 weeks time, and this is a cross section for a perovskite hybrid that we have tried to grow, mainly composed of a hybrid, and means that it has an inorganic frameworks combined with the organic layers. So the message in this slide that I want to mention that be patient if you want to get a good result, especially in using a material growth in this kind of field. You just have to put a lot of patience. And X-ray absorption spectroscopy. This is a very nice technique. In terms of schematic of the instrument, we can divide it into 4 different parts. So first, you need to have an X-ray source. For those who are not familiar with the technique, it requires a tunable X-ray source. So you need to be able to tune or to control what kind of X-ray energies you want to introduce to the system. And then apart, you're gonna have some monochromator to align the things, and some several slits. And the most critical one is the detector. The detector helps you a bit to get an idea, or let's say a response from the material of interest, what it's going to be. So once we introduce an X-ray source, there is some light matter interaction we're coming out from the system. And in the simple schematic, the process itself can be drawn like this. So first, the incoming photon will basically kick out the electron, which is situated in the core level. And then it will coming out to just slightly above the conduction band. And then what happened is that these things, well, it will not gonna stay forever, right? So once it goes down, then it will emit a light. So that's the thing in short what X-ray absorption spectroscopy is. This is a bit deeper about the physics. So all come from the photoelectric effect. As I mentioned earlier, So once of the electron which is close to the nuclei will be receiving enough amount of energy, the electron will expel out from all the orbital lines, and then what will happen that the neighboring shell will basically going down just to fulfill the domain boundaries, right? And how we draw it in terms of the energetic diagram from this paper, we can tell already this is a very element sensitive. So each element has its own energy scale, right? So depending on where you kick the electron, ideally you're gonna notice about the label. So electron that originates come from the KH will essentially go out to quantum level, and then for the LH, that's why for those who are not familiar, when my young student comes, well, just go back again to your chemistry textbook, figure out a bit about how you can identify what all the spectra means. So the spectra itself that I'm going to talk about in the coming slide essentially discuss the observations of this particular regime indicated by the orange block. So mostly we're going to talk about the finding of the rising age. And why is it happen so? Because once you be able to get the right time and the right momentum based on the mechanical quantum physics, that electron will go in the rapid succession. That's why you're gonna see this big jump like that. And this is very how to call very quantum. So a bit about the absorption coefficient, because this parameter will be very useful to understand based on the Beer's law. So depending on how many amount of photon being absorbed onto the material, you can identify based on the number of the mu. So the mu itself, depending on the classified by the atomic number and also the atomic mass. So that's why when you see the plot like this, the absorption coefficient as a function of the energy, they're gonna go like making like all this staircase like a spectral line shape. So this indicating that it has its own a sharp edge, yeah, and it relates to the size of the core level energy of the designated atoms we discussed. This is synchrotron facility we use in SINS beamline. So basically, we're working on tuning the electromagnetic radiations, and all this scheme I took a liberty from my friend's PhD thesis to give you an idea how the X-ray start and goes along the way before entering the end stations. The three parameters that a synchrotron facility has or requires, let's say, it has to be uh, have several sequential mirrors, because all these things is very optics. And honestly, I'm not a optic guy, so I just took for granted how these things actually align. And once actually I learned something very funny story, because during the experiment myself is not really a heavy user, so we just want to be able to join the experiment, but we are not allowed to touch anything. And then once Chishin made some silly mistake, he played around with monochromator, because once I recall that Simon said, don't change the orientation of monochromator in another direction. Accidentally, Chishin received wrong impression, so he moved in the other side. And then all the system got jammed, and we have to suffer like 1 day of the beamline gone for nothing. So for that, that's why Chishin learned in a hard way. We need to appreciate each of the components. And this is only give you artistic view of all of the end station we have. So it has some detector working as an analyzer. This is the way how we introduce a sample into the chamber, and how we play around with the sample using a manipulator. And for those who wish to understand a bit more about XAS, please don't hesitate to read this book. I really recommend, because I enjoying a lot to read the book of Claudia. Give you a bit emphasis of how XIS use to understand the electronic structure of materials. And this is very important because for those who are working in condensed matter physics, the information about density of the state is very crucial. And why? Because the technique span into a lot of application. For example, you can tell from basic science all the way up to the material engineering, you can use this technique as a perfect tool to get an idea of the chemical and physical properties of our materials. Okay. So second technique we use here, I think I will try to speed up a bit because I think I know all of you about PL. Photoluminescence basically govern three different sequential process. One is excitation, in which light is introduced to the sample. You bring some of the electron going up, and then what will happen that the electron will not gonna stay there forever. So it will relax into some uh, vibrational state, and then what will happen that some of the electron will go the intersystem crossing, or sometimes goes directly down back to the ground state, and then you will get some emissions, or basically you hit with a photon, you get a photon. And this is things that you're going to see uh, repetitively in the following slide. So the idea in our project is to use PL to determine the Stokes sieve. So the Stokes sieve is very important for our target because if this guy, the absorption spectrum, is way too close to the photoluminescence spectrum, is not really good. So you're gonna end up with some self-absorption. And for our application in scintillator, it's not really good things to have. Okay, so the message of today, I hope you will have some interest to read our work here in this three nice paper. One is a collaboration work with our team from Poland and from ITS and also ITB. The second paper that we published a couple of weeks ago is discussed about the physical and chemical properties of the cobalt system grown using slow evaporation technique. And then the last but not least is a Tobias paper discuss our main focus for the past years to understand the scintillation properties of the all inorganic copper-based perovskite. So let's go with the first paper. So this is the Ricky. Ricky is the first lead author. He actually the one who come out with the idea to use all these three candidates of the ligands we use for the study. So that I need to appreciate his work here. Okay, so it all started with two works from Croatia back then, and also some work in optical pump spectroscopy. Why we also have some interest to understand the polarons, and then from Croatia, it said that for the lead halide base, we find that this prototypical 2D hybrid perovskite has some indication the existence of small polarons. So all this thing doesn't really survive that long. So it's gonna take us a lot of effort by, for example, using a very advanced terahertz time domain spectroscopy to really get the direct evidence of the charge excitations. So that's actually we use as our baseline how to continue our research direction to have and demonstrate polaric state in low dimensional order. Therefore, we find with using these three nice monster. So for those who know about ionic liquid has this kind of specificity in which you have one heterogonal atoms that normally situated and encountered by, for example, like a cyclic part, and then you're gonna have some very long tails. And we come up with these three different ligands. Uh, the pyrrolinium and imidazole ligand we use to grown a perovskite, and the whole idea that based on Ricky calculations, these three ligand can give you a very nice output to demonstrate the polaronic state of the bismuth perovskite. So this is just give you an idea. This is basic calculation. So before we start, or sometimes we go along the way, we find that the system give us an impression of one-dimensional system. So pretty much it's categorized to what we are looking for. So in the A figure here, this is an illustration where you can have a seed of inorganic part that arranged nicely in one X, and also some are give you impression like this is okay lah one day, but sometimes my student have some problem to understand the B. How come this thing can get you a one-dimensional order? So I always say to him, you're gonna need to look in different kind of representative angle. So you just need to rotate a bit, and you will see this is 1D. So that's one thing that I try to encourage to the student. So first case, we use optics to demonstrate how we can see it. So we collect a collection of UV vis data along with the PL spectroscopy, and then what we found is the following. So it looks like the same, right? But one of the criteria to get the feeling that you do have some polaronic state is you need to get one of the recipe. You need to get the large stock shift. And then it turns out that the following experiment, when we use the time resolved photoluminescence spectroscopy, the collections of the average lifetime we found for these 4 different class give you a very astonishing result. Let me give you a bit, I hope you can see it, but it's a bit too small. So for the first case, the BMP, you get 3.5 nanosecond for the average lifetime. And then when we switch from BMP to API system, there's a reduction on the average lifetime, like 1 order of magnitude. So you get 1.5 nanosecond. That's quite fast. And then suddenly, when you go back to the same system, you keep the ligand the same, but we introduce a small metallic center there. So we mix things up a bit in the metallic part. So we introduce the thin, things get a bit ugly. So we get a bit, how to say, delaying, or let's just getting slow. So we found a 2.6 nanoseconds. And then if we go back to another class of system, it's jump back again. So which mean here, give you, I hope I can give you some bit idea. You tune some on the chemical structure, you end up with different scenario. So we find a situation that based on the chemistry point of view, when you change the cation, the phi, the localized, you change a bit the dynamics of the charge carrier within the system. Yeah. So now we go with the XIS. Here, I said it's element sensitive. So we look the nitrogen elements. All the chemical structure has a nitrogen. So first thing that we need to understand, we collect the information at the room temperature. And then what we found that the phenomena comes from the fact that we see the main transition line that goes very sharp. But if you look, pay more carefully, for the neighboring class, the AP1 system, you have very distinct state here. So this thing associated with the 1sp orbital. So what is the key message from here? The consequences is, that once having a very sharp transition, that the probability of the electron jump to the higher regime here will be compensated. And then when we do the Gaussian fitting, this kind of a complicated number of peaks tells you that once you jump from BMP to API system, you're basically tuning sorry, the initial main transition line. And then when the thing we change to another system by introducing a tin instead of bismuth, we basically change one of the signature here in a small range over here. But for detail, I will suggest please read our paper. And then to understand a bit, we ask our help from Haris, ITB, to calculate the system. And then from the band structure case, all the energy, the band gap, I mean, looks pretty much in agreement to what we found from the UVV spectrum after corrected by Elliott formalism due to the excitonic features. And then the most important is basically on the below panel. And then from this below panel, we try to understand what would be the dramatic consequences when you change things within the ligands. What we found is that once we change the, for example, from the BMP to OP, let's say, here we find an elongations in one of the apical configurations. Apical means when you look from one of out of plane directions. And what will be such a very important, this is what we try to propose. The information we found earlier in the PL data, you see the fast decay time. So we believe that this helps us a bit to understand that the distortion within the crystal structure is being weakened. So that's the reason why we see a fast decay time. Okay, now we go with the, how much time do we have? Still enough? Okay. Okay, then I'm gonna speed up a bit. The, too long. So this is work by Afif, just a bit promotion. So Afif just got recently recruited in one of the top talent in the Netherlands. So he will continue my passion to bring the student to Netherlands. So he will start this semester in University of Groningen. So unlike the previous system, this is, I hope, way much better to look at. So the system comprised of, instead of octahedron geometry, here we are working on the tetrahedral geometry. So the active center here, the cobalt, is being surrounded by 4 chlorine atoms. And then the nice thing with the system, nobody cares at the beginning what's going on with the system. So we ask the simple question as our starting point, what we can learn from it. So what we do is basically, of course, we look UV-Vis and PL. So that's the thing that we do at the beginning before we try to find a more advanced discovery. So in these 4 examples, so I forgot to mention, all this initial tells you the number of carbon within the organic ligand. So MA means you have only 1 single carbon in the organic ligand. The EA means you have 2, and PA got 3 and BA got 4. So as you can see that the shape looks quite weird for the EA. If you look more deeper, you have an extra peak annotated by P2 in between. So this is really painful because we are not actually expecting to see like this. Usually for the hybrid community, we can only be able to deconvolute into 2 things. Then you're gonna have 3 things. Then how we can come out with the solutions? What we do is basically we blame the structure. It's not really a good idea, but luckily we can convince the referee. Well, we are not the first, of course. So we try to get the physical interpretation. It comes from 2 contributions. One is the surface and one is the bulk. And then apparently, well, we got lucky. I remember that this paper is already along the way during the debate. The longest one is corresponds to the P1, is correspond to the surface, and the other one to the bulk. And then what would be the thing in P3 over here? So we I recall again from our, unfortunately I didn't show the XRD. From our XRD, it turns out that the crystal, especially for the EA case, is not really a good crystal. So we are basically relate the situation from the atomic arrangement that the PT contribution come from the defects. And also happening to another case. So just let me give you maybe the time. I will just skip this one. Let's go with the charge dynamics. So let's see what's going on with the charge dynamic profile. In these 4 classes, we find that the contributions of the average lifetime give you in the range of few nanoseconds. The slowest one being held by the MA case. And then the most thing that I want to emphasize is that the component of the tau one is correspond to the fast component. And then what we found is that the fast component for the MA held the majority than the rest. And then we try to explain it based on the case that this kind of a charge dynamic is mainly governed by the theta-hedral distortion. Because here, for the MA case, the distortion is heavily influenced by the geometric constriction. And then, of course, you're going to need some DFT to back up your story. So we give you two conception here that for the band structure, give you the band gap energy of the respective compounds. But the most important one is just to give you an idea that they are basically looks the same. But if you look more close, we have some interest to look on the conduction regime. In the conduction regime, some of the contribution from the p orbital is slightly differs than the others. And then this is the nice thing when you have very nice computation in time is we can actually collect the information of the value of the bond angle. This is very critical because uh, this is the heart of the paper. Based on the calculation, we found that the relationship of the chlorine bond angle behave an oscillatic behavior. So that's why we come up with hello. We get some odd even effect here. So that's why we come out with this paper. Okay, got a time or not? 5 minutes? Then I will sweep forward with the last paper. This is Tobias' paper. He still struggle a lot how to entering NUS, and this is the paper more applied, let's say, on in terms of scintillation. So I need to explain a bit about scintillation in a nutshell. In condensed matter physics, the scintillation is correspond to a physical process in which you have able, when we hit them with the high energy ionized radiation, you will gain or let's say emit UV or visible light. And again, promotion, have looked our review article. This is very basic knowledge for those who wish to know a bit more about scintillators. So we have interest of using this class of material because in the past, copper-based perovskites have been known to compete as a competitor for the lead base that has been become annoying due to the toxicity. And now the reason why we choose the another way to gain to obtain the perovskite using mechanochemistry. Mechanochemical is basically to use a simplified method that I will show you in the next slide. So this class of perovskite structure we use because in the past the system is already quite developed. So this is the synthesis. You pour two precursor, and then after introduce small of acetone, and then you just use a hand grinding method. So it's basically called in Indonesia we call it ngulek. And then after you gain enough good homogeneity in the sample, as shown here by Toby, the before and after to check whether you manage to get the targeted perovskite after we illuminate it with UV light. You will see two astonishing feature in which you emit a blue emissions for the copper after being irradiated with 254 nanometer. So this is how the morphological looks like. So the perovskite doesn't look so nice and smooth, but it's okay lah. Because the most important one here, what we want to mention that we need to know that the compositional ratio is what we are expected, and apparently the ratio is not so bad. Is what we are looking for, 3 to 5. And then in terms of the optical, our product is not so bad after all. Our achievement is basically outperforming the previous predecessor published in these two comparisons because our charge profile can give you close to actually below than 1 nanosecond. So it's not it's quite astonishing. Although in terms of maybe I can skip this one. In terms of what is it? The stock stiff value is quite vary. So here in this paper we are playing a bit with some composition. So we compare between 1D versus 0D case. And then we also at the same in another third class of the system, we replace one of the iodine with bromine. And then apparently by changing this, I call it halide engineering, it can move a bit, goes to lower wavelength. Yeah. So this give you hopefully an idea that by changing a component, you can actually tune the band gap of your material. And for the radioluminescence, this gives you an idea about to identify whether you have some quenching or not at room temperature. So when you are working on the 1D case, you will see immediately that this one figure in the left panel has a different trend compared to the other three cases. And then, in fact, when we look more closely, that all these three other systems give you an idea that both suffering the thermal quenching behavior, which is quite normal. It's not so bad. But the thing that we need to understand a bit more is that when exactly those quenching start to appear. And that's very important for application because we don't want to mess up when we create an acting device. The things suffer from a mechanical issue. Yeah. And I think for the TL, I'm gonna skip a bit more because this is how we understand a bit of chemistry of what we have found. So based on the simplified energetic scheme, all the energy from I took two different cases here for the one substituted bromine and the second bromine. The energy emission is basically doesn't change a lot. It's 2.5 is something. So the thing that good with the calculations is that you can tell already that the angle will give you different story. So when you have a one bromine compared to two bromine, the relationship of having this a single bromine versus two will give you different angle, and different angle tells you about the the deformations. The lattice deformation is related to the optics. So that's how you try to link up the message from the previous data in optic and photometric considerations. I think that's it for me. I hope I still keep up the time. So in conclusion, I just show you of all the three graphical abstracts. For those who wish to learn or to read more, I'll be more than happy to share the papers with all of you guys. With that, I will end my talk. Say terima kasih. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Pak Arramel, for the talk. So we learned a lot about perovskites and also some surface bulk characterization in terms of X-ray absorption spectroscopy and also photoluminescence. So hopefully you learned something and see that how this advanced characterization can really resolve what is happening or what is the structures inside the materials and how this can be used, especially for scintillations. Like I said, this is really an emerging application of perovskites to use it as a scintillations. So it's a very interesting way forward for this material. So I want to open the questions. If any one of you want to ask some questions, maybe I'll start because usually we have to start with something, then maybe someone can follow up. So this XAS, right? I mean, the simple question is it available in Indonesia?
Fortunately, no. Well, the system, as I said earlier, it requires a synchrotron facility. And to the best of our knowledge, our government doesn't really has any keen of interest to invest such kind of expensive equipments. So the best way to do is just approach our friends over there, right? Sending sample, and that's the best thing we can do for now to continue in this research field.
So to Singapore, right?
Yeah,
Well,
yeah.
how long is the queuing? I mean, can
Oh,
they measure for you in like
mm,
1 week or
yeah.
1 month?
The system is very busy. So let's say if you have some good idea, you need to prepare. Let's say have a good time plan because when you submit application, it may take at least another 2-3 months before you start and execute the experiment. So that's one thing that you need to at least took as a precaution manner because it's so busy. It may require some help if your project is very competitive and aiming for very high reputable journals. Then maybe you will need to persuade the director. Okay lah, that's what can be done.
Okay, yeah. So that's a pity, yeah, because I think there are a lot that can be gained from the XCS informations, especially about the materials.
Yes, and one thing that I haven't explained a bit in terms of catalysis, this thing is very versatile. And then we are now also aiming to go that directions because in Indonesia we are very good of making a new idea in invention. The you just to characterize all this thing because we don't really have all the facility we have. I say, well, use the network. That's the best thing we can do now.
Thank you. Any questions from the audience? Anyone before Pa Aziz? Because Pa Aziz definitely will ask a question and it will be a long one. Maybe can you because this is maybe also new for all of us, like these scintillators, right? I mean, maybe if you can briefly persuade us, why do you think that perovskite can be a really uh, intriguing materials for scintillators? I mean, what are there now in for scintillators technology, and why do you think that perovskite is very promising so they can go into this scintillating technology?
Yeah. Yeah. Thanks very for the question. So maybe I will just a bit go to the back when what was it? This one, yeah. So scintillations, why we are so have deepest desire to use it as a scintillator. And if you see on in these illustrations, the most critical issue is just to get a reliable performance of scintillations. And the problem with the past generation, I think now is it already third or fourth. I don't remember by heart. The things with perovskite, you have a very good efficiency of creating the whole charge carrier event. So that's one of the criteria that we why people just go jump all over the way, not only scintillator but also the PV field. They have some very good motivations because all this whole charge carrier is one of the fundamental process that requires to gain access, acting as a scintillator. Yeah. So after you in perovskite, the efficiency of a whole charge carrier formation is quite astonishing. And therefore, however, of course, there is always be an homework to be done. The thing that you're gonna end up, as I showed you to you earlier, it has some defect. So that's still a bit an issue. How we can actually control and regulate the defect states, not to be causing a lot of mess, but still can be tailored in sufficient manners. So this is one of the homework that perovskite still need to outperform compared to the other previous generations. And the good thing with perovskite is easy processable. So what I have shown to you is more like a fundamental growth, but there is also another ways to get you into a perovskite using a very simple solution, another solution process, which is just use spin casting. We will still start to go that route. However, there is still a lot of room to be done because I have also tried use this method back then in NUS, but eventually in the end we give up because the reproducibility is still an issue. I think until now. So I hope that can give you a bit an idea why we also have some good interest in perovskite as a scintillator.
Thank you. Any question from the audience? Pazis?
Myself, not familiar with even what scintillation means. So Does a scintillator basically serve as a sensor?
Uh, yes. So the applications mostly can be used as a sensor. For example, in if you go to the airport,
Mm.
normally we use X-ray detector, right,
Mm.
to look all of our personal belongings, people who
Mm.
commute into the planes, and that's active material. Now they use mainly using a lanthanide-based scintillator. So it's a rare earth element based scintillator. So it's very quite expensive. On the other hand, this kind of approaches is give you a robust access to grow a crystal which is way more cheaper. So the holy grail we want to go is basically to grow this kind of crystal, and we can deposit them into all those thin plates of where is it here in the scintillator panel. So we want to replace, for example, a commercial scintillator based on lanthanide element using this kind of hybrid counterparts.
Okay. Is it that comparing to conventional X-ray photography method, which directly uh, utilizes the penetration of X-ray, and we record the trace on a film. So we insert some additional thing.
Yeah. Yes.
That is this scintillator to I don't know, either to enhance or whatever.
Yeah.
Whatever that causes probably an easier way to get the image.
Yes.
Is that the
So
idea?
yeah. So one of another that's we call tomography. So this kind of applications whereby we use scintillator perovskite base to replace the active agent. So if I remember correctly, yeah, here. This is in the figures. This is one of the example. I think Shishan make a small scintillating fibers
Mhm.
in which the part in the middle we
Mhm.
only use so-called ink type perovskite. So in my case, we use for fundamental science. We need to grow in a
Mhm.
but for this kind of application, we can actually use a solution process. So we just mix things up, but we don't need to create the material into a solid. So here we only use ink-based type perovskite.
Mhm.
So we introduce the material as a solution base at the middle part of the scintillating fiber plane here. Then you can have
Okay.
your active material
Okay.
ready for inspection.
But I still wonder, as far as the use uh, of of materials to respond to X-ray, then the excitation that occurs is from the electrons that are deep down in the core, right? Then, to my thought so far, doesn't it make the process doesn't really care about the band structure, or it's not really sensitive to the band structure. So that means it is not really sensitive to the crystal structure as well. I think that's what the way I'm thinking it, right? So therefore, why would perovskite, yeah, have special advantage for this kind of purpose?
Okay. Thanks for the question. That's a good question. So why we have to so many passion working on this kind of material? Uh, Basic scintillation, as I said earlier, is basically collective process when you emit visible light upon highly energetic radiation, right? So perovskite is so fancy because the active material for the hybrid, right? The inorganic network. So that thing that becomes so peculiar because the network itself can withstand the high impeachment of the irradiations. So, however, there is some limit. So that's the problem with the hybrid stuff. That's what we decided to go along the way to use the all inorganic perovskite. For the all inorganic perovskite, the dimensionality give us a bit of spirit because you can actually channel the highly excited the electron and hole carriers to go in the confined regime. So compared to the the 3D box system, here, for example, in Toby paper, we try to demonstrate and compare when you have 0D of all inorganic copper perovskite compared to the 1D. And then it turns out that actually, if you go too low in terms of dimension, you actually make things worse because the charge carrier dynamic is not so promising for scintillator because in scintillator all things has to go very fast. If you can go beyond then in the regime of picosecond, then we are in the gameplay of the market. So that's the nice thing with the perovskite. So when you change the structure or the dimension, you can actually manipulate the charge dynamic profile of the system.
Okay. But speaking about the structure, the way at least common people understand about the definition of perovskite is simply any material having a structure of AB3, that's perovskite. Of, of course, there is another variant of perovskite which is not exactly AB3. But isn't that factor, I mean, that structure that determines this all superiorities of perovskite, or there are other things actually?
Yes. It all starts with the conventional 3D perovskite. So the perovskite itself start back then in 1979 with the ABX system, whereby you do have the large cation sitting in the middle, and then surrounded by six all the small anionic sites. And then people start realizing, like a Basarov review paper and the rest of the community say that when we try to change the dimensions, for example, from 3D case from the ABX3 goes down to A2BX4 for the 2D case. And then apparently in the same, without changing the type of the elements, means that we only change the dimensions, and it turns out that the charge dynamic profile enhanced quite substantially. However, again, the criteria, as I mentioned earlier, you need to get a very high quality crystal. If we are suffering a very significant amount of the defects within the structure, it really hamper the output of the scintillating properties. So it all starts with the, for example, like cesium, lead bromide, and then after people think that okay, how about if we go with another system, and that's why people now start working on the non-lead system because we want to try to find a way not to use a toxic agent within the scintillators. So this is not a route that we want to go anyway, because at the same time you may also there's some, I call it a trade-off, because when we replace from the PB, which has a very good spin orbit coupling, because that's the thing that's very important to boost up the number of the Hall carrier concentration upon the X-ray irradiation. So that's one thing that in the end we need to, how to say, be grateful, because when you change something, maybe you can enhance, but you can also at the same time lowering another performance. So that's one thing that we try at our best to keep and maintaining the output without sacrificing very significant amount. For example, like light yield that I didn't show because I think it's too much for 1 hour. That's
Yeah.
light yield parameter is also very crucial because if the number of the photon conversions is too low, then it's no point we use this kind of material.
Me, just one more question. You showed us in one of the slides about the one that has polaron discussion on polaron. I was just wondering how maybe okay. First of all, how do you see polarons in experimentally? How do you interpret polarons?
Oh, okay. So, well, we come with a new concept here because I think I need to mention a bit back to the paper of Cortezia. So, for example, in the work of Cortezia here, he used uh, this 2D map where we can actually plot the information that the emission energy uh, is spread as a small contour like within this regime. So for those who not so familiar with polarons, so here we introduce the concept that in 2D case, the polarons can be generated when we have a coexistence of the what we call a self-trap electron and hole simultaneously. And then these two ingredients is already being published by so many groups. So we just took for granted that as soon as we see from the PL signature that the thing we have here, for example, when you see the line shape of the PL at the longer wavelength, is slightly entails to the end of the line, so it doesn't look like symmetrical shape. That's one thing that we can say, aha, so we seems to have a polaron here. Again, this is from previous of finding by Cortezia. So when you see this kind of line shape of the photoluminescence spectroscopy data, that the data start with a very nice landscape, and then all the way at the longer wavelength you see very weird shape. So usually the PL will go symmetric when you have a very nice uh, central symmetric case. But again, in our case, we are working in this 1D class of hybrid. You can actually toying up with this thing. So we actually took for granted when we change the structure, we actually see, that's so bad. We see the shape of this PL. And then when we look the dynamics profile using TRPL, after a bit more analysis, it appears that when you change the structure, you see that the FM behave quite different depending on what kind of things you have in the system. And then the most important issue is that this one, the tau one. Here in tau one, apparently in this case, we do have some bit of struggle when we try to explain to the referee why we only have one fitting. But here you can see already that the PL itself is look like more like symmetric. That's why we don't really think that the number of the polaron here is significantly enough to be analyzed further.
Mm.
I hope that can give you a bit idea.
Not quite yet, actually, but let me continue a little bit. Well, I know several researchers have used the term polaron for different contexts. Like I've heard about magnetic polarons, for instance, and the most conventional one I have understood so far is polaron to be defined as bound state between electron and phonon, right? So, for instance, when we talk about superconductivity, the origin of superconductivity in BCS type superconductivity is polaron, because it has to do with interaction between electron and phonons. So therefore, trying to understand your presentation, it is still difficult for me to connect that polaron with the definition
Yeah.
I have understood so far.
For the magnetic polarance, you're gonna need some lattice deformations to do that. So that's why in the previous work by group of
So it does have to do with lattice deformation,
yeah,
right?
of course, it has to be. We need to uh, take into account the contribution from the lattice deformations, and that's why we do have some hard time to convince the one of the referee because it requires from a very truly single crystal X-ray determinations, which unfortunately we don't have it. Before we publish this thing. But we mentioned that it always good. We cannot always satisfy all the referee questions, and we come out with the bargaining point that from the work by Cortese and all, uh, this class of system have been previously demonstrated. But to really find an evidence of lattice deformation, we cannot escape from the fact that X-ray a single crystal is a must. So that's in that case, we leave it to the editor to decide. We just say that due to the fact that due to the limited infrastructure within our collaboration teams, unfortunately at the moment we cannot answer in satisfaction manner that particular question. But apparently the editor said, "Oh, okay, lah, proceed."
Okay, yeah. As long
In
as
fact, yes,
as
we
long
gonna
as
need a lattice deformation.
yeah, as long as the referee couldn't point to something that I mean to invalidate, right? To rule out your reasoning. Then as long as it is still a possibility, although you cannot really prove it, I mean prove everything, but on the other hand, the referee cannot prove it is wrong either. So
Yeah, so that's why in the end we add how to say a humble statement. We just say indirect evidence. Everyone happy.
okay. Well, for the moment, thank you very much.
Thank you, Pak Aziz. Anyone want to ask questions? Last chance before we close the session. Anybody?
It's not always be a scientific question, right, Terry? You may ask anything.
Can be anything. Yeah.
For your related to how to pursue higher education is also possible. No need to talk heavy business. Go ahead, go ahead.
Percintaan boleh nanya nggak Pak?
Boleh.
Hello, thank you, Bapak. I am Muhammad Aqib. Thank you, Bapa, for the presentation. It was a nice presentation. I am Muhammad Aqib from Pakistan. I am working in the field of perovskites, but I am working on bismuth ferrite for sensor application. And it's really challenging for me to synthesize bismuth ferrite as it is volatile in nature. And I give my third chance for synthesizing bismuth ferrite, but still I fail. I would like if you can give me some suggestion which I can follow up, and I hope it will help me while synthesizing my sample. Thank you.
Okay, thank you for the question. So in your case, it was using what kind of method? Is it hydrothermal or?
I am using sol gel method,
Oh,
Baba.
Soldier. Yeah. Oh, okay. Yes. In fact, that's the reason why I choose this method. Not to discourage your research, but there is a challenge. In fact, Soldier is really, really tough. Uh, the most important one, if I'm not mistaken, yeah, I have a colleague of mine using this Soldier technique. It's not about the hand, but it's more the way how you prepare the high pure grade of the precursor. That's one thing that you need to take things seriously, because once you're working a very small dilution of impurities within your process, it may scrutinize everything. So my suggestion is just pay really attention on high quality precursor you use. That's one thing. And the mixing ratio. Again, that's myself as not really an expert in soil gel, but I just discussed with my colleague who working in this technique. They always keep sharing to us that your guys is very how to say, easy to grow material. But I said not really, because for the cobalt, I didn't mention Afif struggled a lot for the past 4 months to get the good recipe. So we follow one of the recipe from the Chinese team, and it turns out that they miss, or say, or maybe we are overlooked something about the halide ratio. And then once I asked Afif to increase the number of the halide solution to the mother liquids, and it works after 4 months uh, staggering. Because the kinetics, at least for the cobalt, is really painful. Unlike the copper, in 2-3 weeks time you get it in no time. But cobalt, surprisingly, it defeat us almost emotionally, because Afif said he tried everything under the same literature guide. But I said, no, no, no. Now it's time for us to play the devil. So we go in complete different route. So I said, okay, increase the halide, because normally that's one thing we do with Miyasaka when he grown the MRPBBR3 back then. Apparently, this helped us to nucleate the main things we are looking for the single crystal. But for your case, at least two things that you need to take more carefully: the mixing ratio and the purity of your precursor. I hope that can give you a bit of enlightenment.
Yeah, I think my case is also similar with the FIP. I also tried different experimental literature reviews. I followed that very precisely, but I don't know where I get mistake, and till up to now I am not able to synthesize it. I hope after following these precautions, like the ratios and the impurities, I hope it will work for me. Thank you, Baba. Thank you.
Yes, yeah. Just keep trying and try.
Thank you for your questions. Anyone last one? No? So I think we have to close the session. We thank again Pak Arramel for the presentations. Let's give our hand. And as always, we have little certificates. We thank you for giving us this very interesting seminar.